So can you see the screen? Anybody just confirm? You can see the
Yes, sir.
slide. Yeah, good. Thank you. So so we have seen that can how you can given a problem specification, how you can design a digital system that will satisfy the problem specification. So what we'll now go on to do is to kind of design circuits for some standard problems which we encounter commonly and which are often a part of a CPU. So these are things like you have usual arithmetic operations. These are things like usual comparison operations. And for the state machine, these are things like which are called controllers, which helps you execute a program, a high level program step by step. So these are the kind of some of the basic elements of any digital system. In fact, they are common to all digital systems that we'll consider. So before going into this arithmetic operations is the first thing we'll start with. We'd like to do two things. First of all, moment you talk about arithmetic operation, you have to talk about number representation. So how do you represent numbers in a digital system? So that is the first thing we'll study. And next thing we'll see that the moment we go into arithmetic operations and all these things, we need kind of a mathematical definition of exactly what are the kind of mathematical operations. So all of you, I think you are doing your discrete maths course simultaneously with this. So the similar kind of concepts like what's the theoretical basis, what are the axioms of Boolean algebra. So next we'll study that. What are the axioms and how do you represent this kind of mathematical operations? Okay, so these two things we'll study, and then we'll look into some of the implementation issues of building such circuits. Okay, so let us start with numbers, number representation. And we'll do the following. We'll first start with something you already know, which is the Boolean number system, including operations like complementation and arithmetic operations. Then we'll look at some other representation of number which you haven't studied so far, but they are very much useful in various type of digital system. These are things like binary coded decimal, error correcting codes. So it is not the usual Boolean representation. So Boolean representation is kind of mathematical framework where we do, but often we tweak the representation to suit some implementation needs. And you have to go back and forth, map between these different kind of representations. Okay, so let me quickly go through the Boolean representation. So Boolean representation is an example of what is called a radix number system or a positional number system. Okay, so this was one of the earliest development in mathematics, the positional number system. So I think it was as early as 5,000 years or 4,000 years back, I think in the civilization of Mesopotamia. So they started with the number system. And actually they had a very strange, in fact, Chinese also started a radix number system very early, about 4,000 years back. There is a strange way, both Mesopotamia and China, they did not, when they did their mathematical operation, they used this kind of radix number system for adding and subtracting and multiplying. But when they wrote numbers, they did not use a positional number system. They used some symbols. I think India was the first place which used a positional number system, both for writing as well as mathematical operations. Okay, but anyway, I will forget about the history. Okay, so a radix number system represents a number n by this kind of positional value. So it's an it's like there are digits. You have several digits, and digits are positions. And each position has a weight associated with it, tens and thousands and hundreds. And each position, all the digit represents the weight by by which one should multiply the it's the value by which you should multiply the weight of that position. So if we write it, it look like this: am into b to the power m, am minus 1 into b to the power 1 plus a1 into b plus a naught, a minus 1 into b to the power minus 1 for the fractional part, up to a minus b to the into b to the power minus t. So this b is the so-called base of the system. And you see, as you go to the left from a naught, the base value increases in powers. And if you go to the right from the a naught, the position of the decimal point, your base value, not base value, your weight value reduces by powers of 1, 2, 3, and so on. And every position has a digit or a value which is a minus 1 up to a1 and a naught a minus 1 up to a minus b. These are the digits. So basically what you do, you multiply the weight of a position by the digit of that position and then add them all up. You basically get the value of the number. Okay, so few things to be noted. As you can understand, the digit or the coefficient, also sometimes people call it, the coefficient of the highest position, that is b to the power m, and b to the, is called the most significant bit, and the lowest weight position is called the least significant bit. So minus p, a minus p is the least significant bit, and am is the highest bit. Okay, so now these coefficients am to a minus p, they has to be of certain type. So since these are digits, so you know the digits are in a range. For example, in the decimal system, we have digits from 0 to 9. In a binary system, you have only 2 digits, 0 and 1. So the digits ai, am to a minus p, they can only take on a value from 0 to p minus 1. It should be greater than or equal to 0 and less than b, where b is the base. So as I said, if it is a decimal number system, the value of these coefficients can be, and digits can be 0 to 9. If it is a binary system, digits can be 0 to 1. Binary system, the base is 2, so digits can be 0 to 1. If b is the base, it can only be from 0 to b minus 1. Okay, so this is an example expansion or representation. I should not say expansion, it's a representation of 123.45. It's, as you can understand, this is a decimal representation of 123.45. Okay. All right. So as you can see from this expansion, so we have two parts. One part is to the left of a naught, including a naught, which we call the integer part. This basically is an integer part of, so for 123.45, it would be 123. So this is naturally am to the power bm plus a minus 1 to the power bm minus 1 up to a naught. Similarly, you have anything to the right of the 0 position, I mean the ones position, is the fractional part. So here 0.45 would be the fractional part. So that is a minus 1 to the power b minus 1, a minus b to the power b minus b, and so on. So in this case, 4 divided by 10 plus 5 divided by 100. Okay, so these are the usual definitions. I think you are very much familiar with all this. I'm just recapping them. Okay, so this is the fractional part. And as I said, that the common basis we'll talk about is the decimal. which we all work with. Again, this decimal system was started by Egyptians about 5,000 years back because of the fact that we have counted with fingers in our hand. We have 10 fingers in our hand, so it's decimal. Very strangely, the Chinese people 4,000 years back, they used a binary system. So they had a system. Do you know something called a abacus? So some it is present or not, and based on that they did the calculation. That was kind of a binary representation. An abacus is present or not. But of course, they didn't write down the numbers as a positional number system at all. So they used this in their abacus-based computation. Okay, and then base can also be 8 or 16. So 16 is sometimes called a hexadecimal system. So sometimes, since binary representations of moderately large numbers are very long strings of zeros and one, which are difficult to convey, we sometimes shorten them using a hexadecimal representation. The string is shorter. Okay, but binary will use it. There are other number systems possible. So, for example, Mesopotamians, they use a base 60 number system. Base 60, not base 10, base 60 number system. It's kind of they counted the knuckles on the fingers of your hand. So which we sometimes still do. We count on the knuckles of the finger, and somehow I don't know exactly how. If they count all the knuckles, it comes out to be 60. Okay, so in fact 60 is a very nice base because 60 has for all the numbers between 0 to 100, 60 has the highest number of prime factors. 60 has the highest number of prime factors, or no, sorry, not prime factor, highest number of factors. Now, highest number of ways you can factorize the number 60. That has several examples if you use it as a base. I think there is still some rudimentary use of the 60 base number system when you count time and seconds and minutes. So it's there, but its origin was probably due to the counting the knuckles in your finger. Okay, but anyway, I mean, we will primarily be bothered with 10, 2, 8, and 16. And so let us start with the binary. So, for example, if you have the binary number 1101.01, its value would be in decimal 13.25. So because it's a radix number system, the positional number system, it would be 13.25. Okay, so I think this is all child's play for all of you, but I'm just recapping it. Okay, and you should, I think you also know, so two things. First thing is that you should be able to do a base conversion. So if you have 31 or 31.1 in base 4, you can easily find out. So it would be 1 into 4 to the power 0 plus 3 into 4 to the power 1 plus 1 into 4 to the power minus 1. So that would be the equivalent value of this. Okay, so similarly, I think, I mean, just to make sure the kind of computations we'll do, similarly, you can have an octal base 15.2. It just means the number 5 into 8 to the power 0 plus 1 into 8 to the power 1 plus 2 into 8 to the power minus 1. Okay, so I mean, so the reason that the good thing about this positional number system is you just need to mention the base and the digits, and following this expansion, this positional radix based expansion, you can find out the value of the number. Okay. So I mean, this chart will probably help you visualize things better. So these are the numbers. These are the integers in the first how many? 1, 2, 3. First 8 integers. Yeah, first 8 integers in different bases. So in base 10, you can see it's from 0 to 7. Whereas in binary, you need 4 digits actually. So from 0, 0, 0 to 0, 0, 0, 0, 0 to 0 and 3 ones. Base 2, you can see it's from so base 4 can have only 4 digits, 0 to 3. So you see the numbers 4 onward needs 2 digits. So 0, 1, 2, 3, then 1, 0, 1, 1, 1, 2, 1, 3. You need 2 digits. Yeah. Any question? Anybody? Anybody? Any question? Okay. Anyway, let us go ahead. Maybe you can mute yourself if you are speaking. Just a minute. Just a minute. I lost. Lost a lot of things. Hello, CRM. No, I am just teaching. I'm teaching that number theory. Okay. Just a minute, please. Yeah, here. Okay, so this is kind of a nice picture we have of the numbers. So you can observe some patterns. For example, one common thing you can see is that the digits go from 0 to base -1. So the smaller the base, the more number of positions, more number of digits you need to represent the number. And for base 12 and 16, you can see the numbers from 0 to 7 are identical. Also for base 10, they are identical. Also for base 8, actually, they are all identical. Right. So this is something you should keep in mind. This is an example of 16 numbers from decimal 0 to decimal 15. And let us look at, I think it's obvious up from 2, 4, 8, and 10. Let us look at base 12 and base 16. So I would basically like to mention the alphabets that are used, or digits, the symbols that we use for the digits. So for 12 and 16, for 0 to 9, fine, the same decimal digits. And for the base 12, from 9 onwards, you call them alpha, beta, and then it goes to 2 digits. So 1, 0, 1, 1, 1, 2, 1, 3. So the last 2 digits, so it should go from 0 to 11. We have 0 to 9 decimal, and 10 and 11 are represented by alpha and beta. Whereas for hexadecimal, which is more commonly used, the last 6 digits, so we have numbers from 0 to 9, but we have to have numbers from 0 to 15. So from 10 to 15, these last 6 digits are represented by A, B, C, D, D, E, F. Okay. So often what, as I've said before, we'll shorten decimal numbers and write them as base 16 numbers. It's easy to convert sorry, we'll instead of binary numbers, we'll represent base 16 or hexadecimal numbers. It's actually easy to convert from binary to hexadecimal, very easy. In fact, you can just have a small lookup table and do it. And in such hexadecimal number, you will encounter digits like not only 0 to 9, but A, B, C, D, E, F. So so a 16 string of all one in decimal is basically FFFF, which is kind of the largest integer you can have in a C program. Okay, now let us come to some of the basic operations that we do and how to do these operations for a radix representation, a positional representation. So the first operation is complementation, which basically means finding the negative of the number. So so complementation, actually, when we later go to discrete math definition, complementation basically means if you take one value and take its complement, if you add them, they add to 0. And 0 is within quotes. We define something as 0, some element of the number as 0. Okay. And if we add these two, you get that particular element. So that's the definition of a complement. So for usual numbers, we'll deal with 0 is 0, as we all know it. Again, an Indian invention. I mean, others have placeholders for nothing, but they did not use a separate symbol. So Indians were the first to use a separate symbol for 0. Okay, so we'll see how you do a complementation. So first, let us look at the simple case of complementing a single digit A. Okay, so if A is a digit, A prime is its complement. So in base B, it's very easy to get the complement of it. You subtract. So since it is base B, you subtract A from B minus 1. So B is your base. Okay, B is your base. So you take B minus 1. That's basically the largest digit you can have. And if you have a digit A, its complement is just to subtract it from the largest digit. Say, for example, in decimal, if your digit is 2, its complement would be 7. So 9 minus 2 is 7. 9 is the largest digit you can have. 9 minus 2 is 7. So let's see what happens for binary. Binary, the base is 2. The largest digit you can have is 1. Complement of 1 is 1 minus 1, which is 0. And complement of 0 is 0 minus 1, which is 1. Okay, so complement of 0 is 1 and complement of 1 is 0. As I said, it's easy to similar way in decimal. You just subtract from 9, which is the highest decimal digit possible. So complement of 0 is 9, 1 is 8, and so on. Similarly, in octal, where the highest digit is 7, you subtract A from 7. By the way, I mean, if you subtract A from 7, it's not decimal. It's actually the octal representation of complement of A. It's the octal representation. Similarly, in binary, so 0's complement is 1 in binary. 1's complement is 0 in binary. And similarly in decimal. So it's you have to subtract, but the subtraction has to be in that particular base, and the representation you get is also in that particular base. Okay, so octal also you can easily find out such complement pairs. So right now we are talking about single digits. Okay, now let's extend it to a multiple digit number. So let's say I have a number n and I have it's an integer. So I have represented it in base B as am into b to the power m plus am minus 1 into b to the power m minus 1 up to a naught. Okay. So let's so n is this number. We want to find the complement of it. So we have already defined the complement of a single digit. So if ai is a digit, we know how to find ai prime, where ai prime is the complement of ai. Very easy. You subtract ai prime from the highest digit in that base, so which is b minus 1. You subtract it and represent it. Okay, so let's say I form another number m in the following way. So what I do is basically for every digit of n, which is am, a minus 1 up to a naught, for m, I just complement each of the digits. So I replace am by a prime m, where a prime is the m is the complement of am. Similarly, a1 prime up to a naught prime. I just replace it. Okay. And by definition, what is a prime m? It's just b minus 1 minus am. Take the highest digit and subtract. So if you substitute the values for a prime m, you would get b minus 1 minus am into b to the power m, b minus 1 minus up to b minus 1 minus a1 into b minus 1 minus a naught. So this you would get. So if you just rearrange the brackets, you would get m is nothing but b to the power m minus 1 minus 1 minus m. Okay, b to the power m minus 1, b to the power m plus 1 minus 1 minus n. So can anybody tell what is the relation between m and n from this expression? So if we add m plus n, what do we get? We add m plus n. So earlier I said the complement of a single digit is if you add a digit and its complement, you get the highest digit in that base. So if you add 7 with its complement 2, you get 9, which is the highest digit. So let's extend it to multi-digit numbers, m and n, where m I have got just by complementing each of the digits. So what is the relation between m and n? So m plus n is b to the power m plus 1 minus 1. Okay, b to the power m plus 1 minus 1. So can anybody tell what does this mean? For a, let's say 3-digit decimal, what is the complement of a 3-digit decimal if we add to it? 999. Exactly. So you take the highest 3-digit number you can form. If you in whatever base you are, whatever base b you have chosen. So if base is 10, the highest 3-digit number is 999, and m plus n would be that highest number. M plus n would be the highest number. Okay. So I'll not yet call m the complement of n. Rather, I would call m the diminished radix complement of n. We'll call m the diminished radix complement of n. Okay. All right. And we call the radix complement of n, let's say we represent it by n prime, is m plus 1. So you take the diminished radix complement of a number and just add 1 to it, and you get its radix complement. You get its radix complement, right?
So sir, we can't do this for decimal numbers.
Why?
Sir, if we complement.
So what we are doing is that we are replacing its coefficient by its digit complement. So if it has 2, I will make it 7. If it is 3, I will make it 6. Okay, I'll complement each digit. So say for example, take a number. Let's say 234. What is its digit complement? Diminished radix complement for 234. How much will be the diminished radix complement? Say you take a number 786.
765.
765. And you add, so 765 plus 234 is how much?
999.
999 naturally. The every digit we have been called. So this is the, so this 764 is the diminished radix complement of 234, and 765 is the radix complement of 234. 765 is the,
if we have a decimal number and then we take the complement of every digit and we add them, then we won't
add
get
one.
this.
Add 1.
No sir, we add its complement.
No, I'm not getting. So you take a number, you complement every digit, then what you do?
Then if we add both of them, then we will not get b raised to power m plus 1 minus 1.
Will not get b raised to power m plus 1 minus 1. Why? 234 plus 7.
No, sir, I am
how
saying
much?
in decimal number, sir.
Yeah,
I mean,
decimal
after
number.
point.
Oh, no. All these holds only for integers. Okay,
Yeah.
I have not yet discussed the floating point part. So I am discussing only the integer part. Okay, we'll come to, yeah, very right. You are very right. I have not yet discussed that. You just wait. But for the decimal part, does this hold? For the integral part, does this hold?
Yes, sir.
Okay, so one more thing we just define the so this is just a matter of definition. I'm not justifying why this definition or anything. I'm just defining it this way. I'm defining diminished radix is nothing but you just complement, you just flip in binary every digit. And radix complement is you have to add 1 to it, and let us denote that by n prime. Okay, so this radix complement is what we call a complement, usual complement. So I've so far defined it only for the integers. I've not defined it for the floating numbers. That's the decimal part. Okay, so yeah.
Sir, if it comes that write the complement of it, so sir, we will write m or n dash.
See, if we clearly specify it is diminished radix, you should write m. If we just say complement, it would mean n dash.
Okay, sir.
Okay, usually complement would mean n dash. Okay, but again, I am saying this is a convention we are using. Both these definitions are valid. Okay, so okay, so let me tell you the thing. See, these are just conventions in the sense that you adopt some convention, your subsequent arithmetic operations will depend on what convention you have taken. If you keep in mind what convention you have taken and adjust your arithmetic operations accordingly, no problem at all. No problem at all. So it's just a matter of definition, but accordingly you should do your arithmetic operation. Okay, so as it turns out, if you take the radix complement, the arithmetic operations become simpler instead of the diminished radix complement. So the arithmetic operation, in fact, we'll later show the circuits are also smaller. So we'll go by the radix complement. Okay, so let us take the radix complement complement in prime or n dash. So one thing you can see that if you take another number p and p minus n, so this is the reason I am saying that your circuit becomes easier. So if you take two numbers p and n, if you take the difference between them, p minus n, it is nothing but p plus n prime mod of b to the power n. P plus n prime mod of b to the power n for a m digit number, integer, for a m digit integer. It's mod of, so that's a nice property of the radix complement. So basically, the subtraction can be replaced by addition to the complement. The subtraction can be replaced by addition to the complement mod b to the power n again. So mod, what is the meaning of this mod b to the power n? So if it exceeds the highest digit, you take only the remainder upon division by the highest digit. So if we add p plus n prime, and if the summation exceeds say 999, you just take the remainder. How much is excess, that much you take. Okay, because we can only use m digits to represent the number. Okay, so basically, as long as it is within the range of the highest number p minus n, so then no worries, you can directly take it. Okay, so this is the nice property we are looking for. This will be helpful for us in future, because all computers, or for that matter any digital system, when they have to subtract, they complement and add. This also, again, I think all of you know this, they complement and add. So by the way, in your PDS, was number system covered? In your PDS?
No, sir.
Okay. All right. Then I think we can spend some time on this. Okay, so this is a nice property we are looking for. So all we'll do is that given the number n, I will just complement each of the digit, which is very easy thing to do, and I'll just add 1 and everything in base b. Okay, if we do it, it is the same as p minus n, as long as the value is less than the highest number. If it is greater than the highest number, you have to take a mod operation. Okay. So let's take this example. I want to, in decimal, I want to subtract 123 from 321. So I want to compute 321 minus 123. The answer is 198. So let's look at, let's see if we can write it as a complement. So let's complement 1, 2, 3. So the tens complement, diminished radix complement of 1, 2, 3 is 876. 8 plus 1 is 9, 7 plus 2 is 9, 3 plus 6 is 9. It's 876 plus 1, which makes it 877. And now let's see what happens if I add 321 to 876. If we add 321 to 876, you get 1198. And 1198 mod, so its base is 10, and I have 3 digits. So b to the power m is 10 cube, 1000. So 1198 mod 1000, the remainder is 198. Okay, so 198 is the answer. So you can see this is what we have been speaking about. So 321 minus 123 is same as 321 plus 876 mod 1000. Mod 1000, they are the same thing. Okay, so I think this is obvious. This is actually should be obvious.
Sir,
So wouldn't it
here
be
is are there any constraints on P? Like P should have a fixed number of digits or anything like that, or it
Yeah,
is
I
valid
am assuming both P and M, P and N have M number of digits.
But
In
sir,
this case,
why
N is 3.
it should be valid for any P, right? Why only M digits?
Yeah, it is valid for any P. So but only thing is that I mean I think of it this way. I have a digital system which can only deal with 3 digits, nothing more, nothing less. So that's my universe. My universe is 0 to 9, 0, 0, 0 to 999. That's my universe. So everything I write down has to be in this range. I don't know of existence of anything beyond this range. Okay, so all this
Okay, sir.
consistency that has to be in this range. I mean, to the digital world, nothing exists beyond this. If it is
Okay,
m
sir.
bit, is on, no other number exists.
so it should be 877, right, in the third line?
870.
7, like in the third line, because
Oh
3.
yeah, it should be 877. Should be 870. That's a mistake. Yeah, I think the answer is correct. 1198 is correct.
Yes, sir.
Yeah, small
Yes,
mistake.
sir.
Thank you. I'll correct your miss.
Sir, sir, the value of P is not less than 123, sir. Here.
Value up.
Sir, if P less than will, sir, P will be less
Yeah,
than.
then what will happen? Can you tell me what will happen?
Sir, I'm asking for that, sir.
Okay,
Because,
so
sir, because the number goes into less than zeros and negative in.
it will
So
negative. So we'll have a
how we calculate complement, sir, for that?
so
In
we'll
same way,
okay.
sir.
Same way we'll do. But only thing the answer we'll get will be a negative number.
Okay, sir.
Answer we'll get that will be a negative number. Same way we'll do. Okay, so I'll postpone this discussion because so far we have been talking about unsigned numbers and now we are talking of signed numbers. So I'll hold the discussion a little bit. I'm coming to it. I have not yet talked about signed. So I am only talking about positive integers so far. But your question is very valid. We are coming to that. So, but so far, for positive integers, everything is fine. We now know how to subtract numbers. That's all we know till far.
Okay, sir. Got it.
I'm coming to the signed numbers. Okay, so this is another example in binary. So okay, so by the way, you can see the since binary is base 2, the diminished radix complement would be called 2 minus 1, 1's complement. Whereas the radix complement, since base is 2, would be called a 2's complement. So B is 2, so B minus 1 is 1. So the diminished radix complement would be called a 1's complement, and the radix complement would be called a 2's complement for binary. So in decimal, you could
Sir,
have
please
called
repeat
it.
this
Say,
line.
okay, so I have talked about two type of complements. I've talked about two type of complement. You see this slide. I've talked about a diminished radix complement, which I obtained just by flipping every digit, by complementing every digit complement of every digit. And then I talk about radix complement. So radix complement is just you add 1 to the diminished radix complement. Okay. So for a binary, what is the base? Base is 2. So we give a special name. We say the diminished radix complement, we call it 1's complement, basically B minus 1. B is the base. And radix complement, we call it as 2's complement. This is some special name I have given. So this is the general name, diminished radix and radix. For binary, diminished radix would be called 1's complement, and radix complement would be called 2's complement.
Sir, does similarly this thing happens for other systems also?
Other
Uh,
bases?
For example, if I say that 9's complement of a decimal would be a diminished one.
9's complement would be a diminished radix, whereas 10's complement would be the actual
Okay.
complement. So that's the natural definition. You see, suppose I take the number 32. Okay, so or I take the number 3. So the 10's complement would be 7, whereas the 9's complement would be 6. You have to add 1 to get the other. Okay, so let's take this. So these are two binary numbers. So you want to subtract one from the other. This is the answer. And if we take the second binary number, its 2's complement is 2's complement of the second number. So 0, 0, 1, 1, 1, 0, 1, 1. Let's see. Okay, first I have done a normal subtraction. This you can verify. If you convert it to decimal, subtract, and again convert it back to binary, you will get this answer. Okay, so you believe this answer. This is the answer. So it's 0, 1, 1, 0, 0, 0, 1, 1, 0. It's a 9-digit number, binary number. Okay, so now let's see what is the second 2's complement of the second number. So here is the 2's complement of the second number. It's the diminished radix is, you see, all I have done is that I've flipped every bit. So look at the second number which I want to subtract. So it's 0, 0, 1, 1, 1, 1, 0, 1, 1. So how do you get the 1's complement? You flip every bit. A digit complement. In this case, base is 2. So digits complement would be 1 minus this. So basically you flip every digit. So if I flip every digit, 0, 0, 1, 1, 1, 1, 0, 1, 1 becomes 1, 1, 3 zeros, and 0, 1, 2, 0. This is the 1's complement, diminished radix complement. You add 1 to it, get the radix complement or the 2's complement. You get 1, then 1, 3 zeros, 0, 1, 0, 1. So now let's add these two first number and the 2's complement of the second number. You get a 10th digit, which is 1. You get a 10th digit, which is 1. So now you take the mod 2 to the power 9 of this 10 digit. In fact, this should be, okay, mod 2 to the power 9 of this 10 digit. So if you convert to decimal, do and come back to see, we will discuss this later. What basically happens, you can just chop off the most significant digit. Okay, and you get 0, 1, 1, 0, 0, 0, 1, 1, 0. You see, this is same as the answer. This is same as the answer we get by subtraction. Okay, so this is just to illustrate that you can, so basically these complement numbers, so these are kind of, I would not say negative numbers, these are kind of representation of minus operator on a number is same as complementation. And basically we don't need a circuit for subtracting, we only need a circuit for addition. Okay, so this is some representation. So this is, you can see the two like this is the diminished radix. So the first one is the first column is the binary number, second column is the diminished radix, third column is the radix complement. So these, I think these are some examples. You can check that how we have got it. So the ones complement we have got by flipping the just a minute. দিচ্ছি আমি নিয়ে আপনাকে ফোন করছি কেন আমি শর্টে কিছু আচ্ছা আমি ক্লাসে পরে ফোন okay sorry for the disruption. Okay, so what you see, we have done something very simple. We have basically complemented every bit and then added one to it and take the modulo this is how much, so modulo 16, so the highest digit is 16, so you take a modulo 16 operation. So that's all we have done. Okay, so I'm not going through this example, you can actually check it. Maybe as an exercise you can do it. Okay, so these are everything. So examples of the rules we have spoken so far. Okay, now let's go to the next important operation, which is we want to convert between bases. So why this is important for a digital system? Of course, from a mathematical point of view, this is very important. But why for a digital circuit view it is important? Because often you see sometimes different parts of a digital system, they operate on different number systems. For example, you are sensing, so the velocity sensor or the speed sensor, speedometer of your car, maybe it's an analog system and it represents number in decimal. Whereas in the CPU that is sitting inside your car, maybe that does all the decimal operation or hexadecimal operation. So moment this one system, the CPU has to process the data obtained by the speedometer, you will need all this base conversion. So in fact, we'll kind of build digital circuits which will do this base conversion. We will see nice digital circuits for doing this base conversion. So these are kind of very, very common part of digital systems. Okay, so let's look at the rules for this base conversion. Okay, so suppose I want to convert a number in base B1 to its representation in base B2. So if B1 is less than B2, so if you are converting from a lower base to a higher base, for example, if you are converting from base 2 to base 10, so for all your arithmetic, you can use the base to a higher base B2 representation. Okay, you can use the B2 representation. Okay, so what does this mean? So this basically means that so let's give an example for this. So suppose I have a number 432.2 base 8. I want to convert it to decimal. So B1 is 8 and B2 is 10. So maybe I can use the arithmetic of base 10 to do this conversion. So let's see what does this mean. So this basically means that I'll just use this formula. This basically means I'll just be, you see that what I'm basically doing is that I'm just expanding 432.2 base 8 using decimal arithmetic, using base 10 arithmetic. So I have just multiplied 4 into 8 square, 3 into 8 to the power 1, 2 into 8 to the power 0, plus 2 into 8 to the power minus 1. I have just done that, nothing else. So binary to decimal or octal to decimal, these are very simple. You have to just write down the expansion and compute this expansion in the higher base, the decimal base in this case, and you get the answer. Okay. So any doubt? I'm sure there will be doubt here. So any doubt or argument, argument against my argument? Anybody? Is this okay? This is kind of all I'm saying is a simple rule to convert from a lower base to a higher base. Okay, you just expand. Basically, you just expand the number and do all your arithmetic in the higher base. So in this case, in decimal base. Okay, so another example. So I want to convert binary 1101.01 base 2 to decimal. So all I will do is that do the decimal arithmetic considering the base of the binary. So this is a small problem here. This will be 2 cube, not 23. This will be 2 cube. Okay, fine. So this is simple. I think this much all of you know. Okay, so now let us look at the other way around. That means I want to convert from a higher base to lower base. For example, I am to convert decimal to binary.
The fractional part you could explain.
For this higher base to lower base.
Yeah, the previous slide.
Oh, okay. Yes. So the fractional part you can see is that you starting from your decimal point or starting from your point, I will not call it decimal point, starting from your point, you go to the left, you keep on increasing the powers of the bases. You go to the right, you keep on decreasing the power of your bases. Keep on decreasing the power of your bases. Right. So one thing, by the way, let me ask this question: that do you think a number which is not a recurring number, recurring decimal, so there's only finite number of decimal digits. So if you convert to a higher base, is it possible to get a recurring or continuing fraction number, or you will still have finite number of digits after the decimal point in a higher base? So can anybody answer this? So I have finite number of digits.
It can change to recurring.
It can change to recurring even if we convert from a lower base to a higher base?
Yes, sir.
Yes, sir.
Can you give an example?
Like for 1/3, if we start from ternary, it will be
No.
0.1.
I am converting a lower base representation to a higher base representation. So you want to give an example?
Yes, sir. From base 3 to base 10.
Right, exactly. Right. So tell me. Yes.
So for base 3, 1/3 will just be 0.1. But in base 10, it's recurring.
Correct. Very good. Thank you.
Sir?
Yeah.
Sir, in the previous case, let us say B2 was not 10.
B2 was
something greater than 10 means we are always converting to decimal, so this is a one-step process, right? Let us say we had
anything in a higher base will be a one-step process.
Like let us say we want to convert a base 8 number to a base 12 number. Then how to do in one step?
Exactly.
We have to,
Yeah. So how to do in one step is this. See what you are doing. You are taking every digit of the lower base and multiply it with the weight of that position in the lower base. The weight of that position to the so say 1101. The weight of the most significant bit is 2 cube 8. Okay. So all you do is you take the base 12 representation of 8. I'm converting decimal to base 12. I'll take the base 12 representation of 8, and this 1 or 0 I'll multiply with that. 1 or 0 I'll multiply with that base 8 representation. So when you add this all up, sorry, not base 8, base 12. When you add this all up, you will get a base 12 representation. For example, say for example, suppose I have a so in 2 cube it will not happen, but say let's say 2 to the power 4. 2 to the power 4. 2 to the power 4 also it will not. In this case it will not happen. But suppose you are converting to hexadecimal, so 2 to the power 4 would be f. Oh, sorry, 2 to the power 4 is not f. 2 to the power 4 is 1. Okay. So basically what I am trying to say is that this arithmetic, let me think what will happen. This arithmetic will be in the higher base. So CRM, what should be, how should we go about it?
No, that is correct. What you said is correct. So it's a question of, say from 8, base 8 to 12, if you can do the arithmetic in base 12, it will work in the same manner because the definition stays the same.
Yes, but only thing, maybe we should work out an example, maybe in base 12, because all this multiplication and everything has to be in base 12. So maybe the digits will change. Maybe the digits will change. Okay, so that's what you have to do. Okay, yeah, it's a very good question. In fact, we have not worked it out. Maybe in the next day, or I'll upload an worked out example from a say base 8 to base 12 conversion using this rule. But okay, let us believe this for the moment, and it will actually work out in the same way. Maybe I'll give an example of the steps. Okay, now let us do the conversion other way around. We want to convert from a higher base to a lower base, for example, from decimal to binary. Okay, so now things are a little bit complicated in the sense that earlier only multiplication and addition was enough for base conversion. You only need to multiply. So power is basically multiplication. Multiplication and base addition is enough for base conversion. But now you will need division also to do the base conversion. You will need the division operation to do the base conversion. Okay, so let's try to derive that. Let's take a number n in base b1. b1 is the higher base, the decimal. So let's take a number n in base b1. Now you split it into two parts. The first part is the integer part, call it a. And the second part is the fraction part, call it b. Okay, so the the part A, it is very easy to do it. So it's very easy to do it. So let's go it by this way. So what we do is that with the part A, I divide every term by B2. B2 is the higher base. Okay, so if B2 is decimal, I divide every term by 10. Every term in this sum by 10. Okay, so what do you get? You see that basically the values, the coefficients, we can again split into two parts. One part is Q0, which is AM with these coefficients or with these weights reduced by power of 1. Sorry, reduced by 1. The power is reduced by 1. So AM B2 to the power M becomes AM B2 to the power M minus 1 and so on. Okay, so it's so this process, when you do to decimal to binary, you will see that this is not such a complicated process that appears from this equation. But so the last digit becomes A0 by B2. Okay, the least significant digit becomes A0 by B2. Okay, so
sir, you said that B2 is the higher base, but you have written B1 is the higher base.
Oh, sorry, B1 is the higher base. Wait. Yeah, B1 is the higher base. Sorry, if I said that, it's wrong. I'm converting decimal to binary.
Okay, sir. Okay, sir. Yes.
I'm converting decimal to binary.
Sir, so n subscript b1, shouldn't it be a expansion on b1's power?
No, NB1 is number in base 1, and what you have on the right is the number in base 2. So this is basically binary to decimal. You are doing the arithmetic, you are using the arithmetic of B1. That is exactly what was done in the earlier slide.
Okay, sir. Yes, sir.
Yeah. So if B1 is decimal and B2 is binary, the left hand side is the decimal number, right hand side is the binary number, binary representation. Okay. So B2 is 2, B1 is 10. Okay. So you see what you have got, the least significant digit is nothing but the remainder on dividing A0 by B2. Okay. So basically what I am doing is that I am dividing the integer part by 2. Dividing the integer part by 2 to get Q0. To get Q0. Okay. So the Q0 is the quotient and A0 by B2 is the remainder. A0 by B2 is the remainder. So so basically, so the least significant digit of A B2 will be the remainder on dividing A0 by B2. Will be the remainder on dividing A0 by B2. Okay, because see finally, so suppose you want to do a base convert. So what is our goal? Why I have written this equation? So I am given in B1. I'm given the digits in B1 representation. I want to find A minus 1 up to A minus P, because those are the binary digits. Okay, so I am describing a way to find this AM up till A minus P given N. So I want to come up with an algorithm. In order to derive the algorithm, we are just looking at this expression.
Sir?
Yeah.
Sir, A0 would always be less than B2.
A0 will always be less than B2. Yes, A0 will be less than B2.
So, sir, how a fraction can be remainder, sir?
Yes, exactly. A0 will.
Sir, why
always...
A0 is less than B2? A0
yeah,
can
so
be
CRM, what is the answer? Maybe CRM, you can tell what is the answer.
Let me just see.
Yeah, you are perfectly correct. In fact, let me think. I have to think and tell you the answer. Maybe you can also think. Yeah, A0 should be just A0. A0 should be just A0. Because the main problem is we are in the left hand side, we are doing a B1 arithmetic. And in the right hand side, we are doing a B2 arithmetic.
Sir, a remainder of A0 by B2 will be A0. Means what's the problem? Like division.
Yeah. Right. You are right. So that way it's correct. So if A0 is less than B2, remainder on dividing A0 by B2 is A0. Yeah, that's correct. That's correct. So let's go ahead with that. We will maybe let us see why you have written this notation. We will later figure out why you have written this notation. Okay, but okay. So basically it is correct. A0 by B2, the remainder of A0 by B2. So A0 mod B2 is same as A0 if A0 is less than B2. Okay, so let's live with that for now. Okay, so again, let us make our goal clear. So what I am given is I am given n in base B1. So basically, I am given the digits of n in base B1.
Just a minute. See, here we are trying to get see the least significant of digit of A in base B2. Okay, so if you are doing decimal to binary conversion, then you are basically dividing by 2, isn't it? So this is like decimal to binary conversion. That means you are converting from a higher base to a lower base. So that is how this conversion is going on.
Yes, sir. So the least digit would be means A divided by B2's remainder would be A naught.
Yeah, so that is what is happening. That is exactly it. So least significant digit of A in the number system B2 in base B2 is the remainder of A0 by B2.
Sir, A by B2, sir.
Huh?
A by
A by
B2.
B2.
Yeah. A
So
by
see,
A
I
by
think
B2.
the
No,
fundamental
just a
question
minute.
is does this identity hold? So A by B2 in
Yeah,
base
A by
B1,
B2.
does it equal to Q naught plus A naught in base B2? This identity does it hold in base B2? So A by B2, base B2, is it same as Q naught plus A naught in base B1? In base B2. So A by B2 in base B1, is it same as Q naught plus A naught in base B2? That's the question. Yeah, it should be same because of the reason that A naught is less than B2. Okay. Okay, so this you should keep on doing recursively. So first you get A naught. So how do you recover A naught? Basically, you divide N by B2. You divide N by B2. Whatever is the remainder for the integer part. I'm only processing the integer part. So to get your A naught, what you have to do, you have to take the integer part of N, divide it by B2, you get a quotient Q naught and you get a remainder A naught. So use the remainder as the least significant integer part of your representation in base B2. Basically, if you are doing decimal to binary, it's the least significant binary digit for the integer part, and Q naught is the quotient. And now on Q naught, you again divide Q naught by B2, and same way you get A1, and you get say Q1, another quotient. So Q1 again you divide by B2, you get A2, and so on. So this you keep on doing recursively until the quotient becomes 0. Until the quotient becomes 0. Okay, so this is the usual decimal to binary conversion process. Usual decimal to binary conversion process.
Sir, I did not understand why A naught should be less than B2.
Because any digit in a base B2 has to be from 0 to B2, 0 to B2 minus 1.
Sir, but A0 is in base B1, right?
No, A0 at the, see, I want to convert N to base B2. So AM, A1, A0, these are digits in base B2. I want to find them out.
Sir, but if we are trying to convert from B1 to B2, so we are already using the expression on the right hand side. You can see it is in terms of B2. So if we already know that, then how are we?
Yeah, no. See, so okay. This equation, this identity holds or not? This holds. Suppose B1 is any base and B2 is any other base. This left hand side equal to right hand side. I can already write down. Only thing is that I don't know what is the value of AM, A1, A minus B. I don't know their value. But this equality I can always write, whatever be the basis. See, that's the definition. That is what is meant by
No,
base
Pavitra,
conversion.
I think let us go through the examples in the
Example,
next slide.
yeah, that will be
We
better.
can come back to this later.
We will come back. Let us come to the example. All right. So let's say I want to convert from decimal to octal. So 548 decimal, I want to convert to base 8. Okay. Okay. So if we divide 548 by how much we should divide? We should divide by 8 because B2 is 8. Okay, B1 is 10, B2 is 8. B1 is 10, B2 is 8. So we should divide by B2. 548 we should divide by B2. So if we divide 548 by 8, we get a remainder of 4. and we get a quotient Q naught as 68. All right. So our first least significant digit in octal would be 4. Would be 4, A naught. That is A naught. Okay. So now again divide 68 by 4. Divide Q naught by 4 to get Q1 and R2. So if you divide 68 by 8, you get a remainder of 4 and you get a quotient of 8. So the next significant digit of the octal representation would be 4 again. Now divide 8 by 8, you get a remainder of 0 and you get a quotient of 1. So the third least significant digit of, okay, sorry, it's least significant digit. I'm going from least significant digit side. So the third least significant digit would be 0 again, and I get a quotient of 1. I divide 1 by 8 again, I get a remainder of 1, get a quotient of 0. Since I've got a quotient of 0, I can stop the procedure. So the 4 digits, remember I've got the digits from least significant to most significant order. So the octal representation would be 1044. Octal representation would be 1044.
Sir?
Yeah.
So if the 548 was in base 12, so what will do then?
Okay. So if 548 is in base 12, then you have to divide. Okay. So
no. In that case, you can just evaluate it in base 12 arithmetic. You can just evaluate the thing in base 12 arithmetic.
Yes.
Means first we have to convert that base 12 to base 10?
No. See the definition. See, if you go back to that slide, that where you have written NB1, okay, NB1, what it says is use the arithmetic of base of B1. So it is. So what is this thing?
Base B1 is 12.
548 to the base 10 is basically 5 times 100 plus 4 times 10 plus 8. So now all of that you can that arithmetic you just need to do in base 12. That's all. That arithmetic you can do in base 12.
Okay, so that is little bit maybe counterintuitive right now to how.
No, it is not counterintuitive. It is the definition only. Only thing is that you do the arithmetic in base 12.
No, not
because all those see, because the base is higher, all those digits have direct representation in base 12. So you just need to do the arithmetic in base 12.
Yes, exactly.
Sir, can you show that? Means I am still unable to understand how we'll do that.
Well,
okay, let me see.
You just evaluate it. You just evaluated it. So the difficult part is actually you'll have to do the arithmetic in base 12. That is the only thing. So in base 12 arithmetic, so 8. Now if you do 4 times 10, okay. So 4 times 10 in base 12. You'll have to do in base 12 arithmetic. I've not done that. Okay, I'll have to do it and show you. I'll have to work it out on paper and show you. It is not there in the slides right now. I'll work it out and
maybe we can upload a PDF later showing that example.
We can put it in the next class. Immediately I don't have it. Yeah.
Thank you, sir.
Yeah, maybe yeah. It's bit
tricky, I think a few corrections may be needed. Yeah. Okay.
Yeah. Maybe we can update the slides and then upload the slides.
Yeah. Okay.
Okay, so this is the base 8. So let's take another example. So I want to convert 3, 4, 5 base 10 to base 6. So I do the same thing. I divide 345 by 6. I get a quotient of 57, get a remainder of 3. And if I follow the same way, so I get 133 base 6. 133 base 6. Yeah, but so the only thing we are meaning to tell is that the base 10 operations are fine, but what is the arithmetic in some other base? We have to think of that. Now let's come to the fractional part. So here we do the processing in the other way. So the fractional part, let's say, is a minus 1 b to the power minus 1, a minus 2 b to the power minus 2, and so on. So we'll recover in the opposite way. We'll recover first a minus 1, the most significant fractional part, then a minus 2, and lastly a minus b. Okay, so I'll explain it with that. So basically you can imagine what you have to do. If you want to get a minus 1, you have to multiply by b2. You have to multiply by b2. Okay, so you get a minus 1. This will be a minus 2. There is a small correction. It will be a minus 2 b to the power minus 1. The part within f. And similarly, recursively you continue. So let's take an example. So it's 0.3125 base 10. I want to convert to base 8. So I multiply 0.3125 by 8 because now we have to multiply. So you get 2.500 in 2.500 in decimal. Okay, right. So what you do, you keep the integer part, which is 2, and you take the fractional part out. You look at the equation. You take a minus 2. That's your next digit you get, and the remaining part is f, the fractional part. Okay, so f in the first line of the example will be 0.5100, and a minus 1 in this case will be 2. So a minus 1 is 2, f is 0.500. Multiply that by b2 again, so 0.500 into 8 again, you get 4.000. Integer part is 4, that's your a minus 2. The f part is 0.0000. All right. So as long as the f part is non-zero, you keep on doing this recursively. As long as the f part is non-zero. So we have seen in the second step only we have got the f part as 0. So our a minus 1 is 2, a minus 2 is 4. So 0.3125 base 10 is 0.24. We write this 0.24 to denote that this part is the fractional part. 0.24 base 8. So the reverse process, you keep on multiplying, retain the integral part, and the fractional part you multiply again by 8, just like we are doing for quotient and remainder. Okay, so basically given a decimal, a floating point number, I'll not say floating point number, given a number which has both an integral and fractional part, we have to process them separately by these two different things and get the answer. Okay, so should we go into this today? CRM, should we go into this, or you want to complete
Which one?
that?
No, you can just do the. I mean, we'll not go into double. Just we'll stop before double.
All right. So different radix number systems, base 2, base 12, base 8, how to do addition, how to do subtraction, how to do complementation, and how to do a base conversion. These things we have studied. Now we'll come to a number representation, which is slightly modified form of this radix representation. Radix, slightly modified form, because it has some advantages, this modified representation. So this representation is called a binary coded decimal, or BCD, binary coded decimal, right? So we will see how do we
Pavitra, have you got muted?
Can you hear me?
Yes, sir, we can hear you.
Yeah, can you hear me? Maybe I lost connection or something.
Yeah, you're audible.
I'm audible, no? Okay, let me quickly share the screen. In between, I lost connection temporarily. Just a minute. Just a minute. Yes. So let's see how do you get this BCD representation from a binary representation. So for numbers 0 to 9, for numbers 0 to 9, the BCD and binary are identical. BCD and binary are identical. For numbers from 10 to 15, one goes to the next higher place and d minus 10 in the current place. So let me give an example. So let me give an example. All right. So first let me state these two rules and then I'll see. I'll show you how to do that. Okay. So for number d, which is between 0 to 9, so binary and BCD are identical. For numbers from 0 to 15, 0 to 15. So okay, let me first tell the basic motivation of using BCD. So basic motivation of using BCD, a set of 5 bits, sorry, 4 bits, a set of 4 bits. You can so if you want to represent decimal numbers from 0 to 9, so how many digits will you require? How many binary digits will you require? How many binary? It's a question to the student. Suppose I want to represent a decimal number from 0 to 9 using binary. How many binary digits will I require?
4.
4. Okay, so it's not 3. Using 3, you can represent only up to 7. So it's 4. But the thing is that there are some because the decimal digits can only be from 0 to 9. Can only be from 0 to 9. But using 4 digits, you can represent from 0 to 15. You can so there is some kind of redundancy. So if you use 4 digits, there is this unused 6 number, not 6. How many? There is this unused 6. Yeah, unused 6 number of combinations of these 4 digits, 4 bits, for which there is no decimal digit. There is some kind of redundancy. Yeah. Okay, but maybe we let's live with that redundancy. Because anyway, you can only use 3 bit and then, or you can use 4 bit. So 3 bit is insufficient. You have to use 4 bit, but 4 bit is kind of over sufficient. And in the sense that you only need to represent 0 to 9. So the remaining numbers from 0 to 15, they are excess kind of. We don't need them, but anyway, we have them. So what do we do with these extra bit combinations? So basically, what happens for the decimal numbers 0 to 15? If we look at the binary equivalent of the decimal numbers 0 to 15, so what do we do with those combinations? Okay, so the thing is that, yeah. Okay, so the thing is that this 1 goes to the next higher place and d minus 10 is in the current place. We will come to that. Let us tell another rule for doing this. So if you have a number D, if you have a decimal number D in this range 0 to 15, what we do, you add 6 and take mod 16 of the entire thing. So if the decimal number is more than 9, you add 6 to it and take mod 16. So can you tell what is the BCD representation? What is the BCD number for 12? How do you get what is the BCD representation for 12? For the decimal number 12, what will be the binary thing? So you add 6 to 12, you get 18. Take mod 16, you get 2. You get the binary representation for 2 and consider that as the BCD representation for 12. Consider that as the BCD representation for 12. Okay, so this is 12. You add 6. You add 6 and take modulo 16. So basically you get 0, 0, 1, 0, which is 2. Okay, so let us look at this chart. Let us look at this chart. So what with this operation, you can let us observe a pattern and then we'll tell about the algorithm. So what we are doing is that so this operation is fine. So we are adding 6, then taking modulo 16, and whatever is that, we get the binary representation for that. So this can actually be done in a simpler manner. You can, if you handle the bit sequentially, you can add 3 instead of 6 and then shift to the left. You will get the same answer. Add 3 and then shift to the left. Okay, so this forms the basis of a much more complex algorithm called the double. We'll do that in the next class. But first look at this. So let us look at this. Do we have an example of? We'll go into all this later. Let's see an example of the table of binary numbers and corresponding BCD numbers. Yeah, forget about this XS3 cyclic gray. Look at the first 4 columns. Look at the first 4 columns. Okay, so these are the BCD representation of the numbers 0 to 10. These are the BCD representation of the numbers 0 to 10. So you see first 9 are same. 0, 0, 0 is 0. 0, 0, 0, 1 is 1. 0, 0, 1, 0 is 2, and so on. Up to 9 is 10 is same. So 0, 1, 1, 1 is 9. But after that you see something else happens.
So 0, 1 is 7, right?
Oh, sorry, 0. Okay, so this is up to how much? This is up to
9.
This is up to 9. This is up to 9. Oh, sorry, this is up to 9. Okay, right. From 0, 0, 0, 0 to up to 9 we have. Okay, so up to 9, as we have said, binary and BCD are same. Binary and BCD are same. So beyond 9, other combinations. Say for example, if you have a combination 1, 0, 1, 1, that is not the right BCD representation. That is not the right BCD representation for 10. You have to find it some other way. Okay, so we'll go into this. We'll go into a proper algorithm for converting this, but maybe in the next class it will require some bit of time. It will require. So CRM, would you like to quickly complete the CMOS part?
Yeah, I was just working. So maybe we can just try to work out that conversion from 548 to.
Yeah, let us work that out. So do you want to share a external and work it out?
Yeah. I'm just pasting one link so everyone can open that.
No,
link.
maybe you can share your screen. That will.
No, I'll share.
Oh, you want to not want to do that? Okay.
Yeah, I've shared one link. You can.
Okay, I'll open that link.
Yeah, you can open that link and share. Okay, you can share that also. Everyone can open that. All right. So
I'll open that link and maybe I'll share the screen. Let us.
Yeah. So if you open that link, you basically get a multiplication table for base 8, which is a little helpful. So now if you, so what you want to do is, okay, let me, yeah. So what you want to convert is that 548 to, in base 10 to 12. So 548 is 5 times 100 plus 4 times 10 plus 8. All right. So 4 times 10 is basically 4 times A. Okay. 4 times A. And if you compute that, it is 34 in base 12. You can just consult this table. It is 34 in base 12. And 5 times 100. So now 100 is A times A. So A times A is 84. Okay. So if you multiply 5 by 84, if you just do that multiplication, 5 times 84, let me just see, yeah. So 5 times 4 in base 12 is 18. If you consult this table, 5 times 4 in base 12 is 18 and 5 times 8 in base 12 is 34. So if you do the addition in base 12, it turns out to be 385. Okay.
So this is a multiplication table.
In base 12.
Okay.
So now you can add 385 and 34 and 8 in base 12. So let us just try to do that. 358 plus 34. You can do it on your own. I'm also doing it now only. So 8 plus 4. 8 plus 4 is 12. So 12 is basically in base 12. What will be 12? 12 will be 10, right?
Yes.
12 will be 10. So 5 plus 1, 6, 7, 8, 9. So it is 90. So 358 plus 34 is 390. Now to that you add 8. So it is 398. So yeah, so the conversion of 584 to base 12 is 398. If you do the arithmetic in base 12. All right. So are you able to do? You can just do it yourself and say.
Yeah. Maybe they can use this multiplication chart and.
No, I use this multiplication chart only. I think we'll have to improve the slides. I mean,
we'll include them in the slide. We'll include them.
This conversion is fine. Only thing is that you have to use this. You have to do the arithmetic in that higher base. So you'll need such a table, which can also be constructed. I've just used it from the internet.
Yeah, this can be easily constructed. Anyway, I think CRM, let us stop today.
I just covered that part on CMOS. We'll finish that part. Let's not leave that pending. So okay, so you can stop sharing your screen. I'm not. Yeah.
I am allowing you to do that.
Okay. Yeah. Oh, yeah, just I wanted to ask, so could you do that conversion? Yeah. Hello?
I have not done yet, but
no, I'm just asking the students. I'm just asking the students. Hello?
Yeah, please respond, people.
Could you
so
do that?
From base 12 to base 8? Yes, sir, we have done the base 12 to base 8.
Yes, sir.
So
can anybody of you?
No. it was that we were trying to convert that 548 in
Yes, sir.
decimal
Yes.
to base 12.
Yes, sir.
So did you also get 398?
Sir, 548 in base 12 is equal to 1410 in base 8.
No. 548 in base 10. 548 is in base 10. That is what you had in the slides. Someone asked at that time, right?
Yes, sir, it was in the slides. Base 10 was clear, base 12 was not clear.
No. 548 in base 10, we want the corresponding value in base 12. Okay, I'm just sharing my screen. Maybe it will be. Are you able to see my screen? Hello?
Yes, sir.
Yeah, we can see.
So yeah, so that so it is 548. Just leave this part. So so this we want. This is 5 times 100 plus 4 times 10 plus 8. Okay. So this 4 times 10. This I've done here. All right. 5 times 100. This is 5 times 100. 100 is 84. If you consult the table, 100 is 10 times 10. This 100 is
84, yes, sir.
10 times 10. That is 84 actually. So I'm just writing as 84. Yeah, that you get from the table, by the way. That is A times A. All right. So this is, so now I multiplied 5 by 100. This is 5 times 100. So, oh, sorry. This is not correct. This is the whole thing. Yeah, this is 5 times 100. This is what I get. So I'm doing the addition in base 12. Of course, this addition in base 12, this is in base 12, by the way. These are all in base 12. This is basically 340 in base 12. So, yeah. and then I've just added this addition I have done. All right, so just do it yourself and satisfy yourself that you get the same result.
Sir, once can you show the conversion from base 12 to base 8 also?
Base 12 to base 8. Base 12 to base 8, you can do division. Actually, division you can do even if you want to. See, both the methods work the same. It is just a matter of convenience. Which one works better for you? So you can so both ways are actually remaindering and this multiplication. Both the methods will give you the same result. So it is just a question of which arithmetic is convenient for you.
Okay, sir.
Yeah, results will be the same. All right, so let us just go over to the other slides. We'll just complete the earlier thing.
How do you multiply in the base?
can you speak a bit louder?
Like sir wrote there 3 into A, so how is that calculated?
Yeah. So CRM,
Which one? Which one? Just, yeah, I couldn't hear you. Can you just repeat your question?
Sir, 4 into A, how is that calculated?
4 into A, just look at the table. Look at the table.
So you used a multiplication table. There's a link in the chat box. You open it. There's a multiplication chart.
I think I got it open. I'll just show it to you. See, 4 times A, it is 34. That's what I've put there.
Understood.
All right, let us just complete this part. So, yeah, so I think these circuits you can do. So, did you try to work out the theorem which I wrote last time? Anyway, that will be given for your exercise. So, okay, let us just look. This is a interesting gate. It's called the CMOS transmission gate. So, and let us just see how it works. So now, so we'll use the same principle. Suppose A is high. You consider the situation that A is high. Okay. So let us consider the situation that A is high. Let us call it high. So say 5 volts. So if A is high, now you consider so you consider the situation that A is high. Okay. A is high, and here you have two possibilities for B, for S. Say S is equal to 0 and S is equal to 5 volts. S is 0 and S is 5 volts. So all right, so let us just so when S is 0, let us call this T1 and let us call this T2. All right. So when S is high and when A is at 5 volts and S is 0, so here S is 0. So let us see. So S is 0. So S bar is, let us say, high. So here it is 5 volts. S bar is also 5 volts. All right. So in this situation, there is no channel here. All right. There is no channel here. So T1, I'm just saying cross T1. T1 is off. All right. What about T2? T2, this is at 5 volts, this is at 5 volts. No potential difference. So T2 is also off. All right. So now this overall transmission gate is B is like I'll say open. B is open. There is an open circuit between A and B. So I can write open circuit. Let me just move this a little bit. So there is an open circuit between A and B. All right. And consider the other case when S is at 5 volts. So if S is at 5 volts, here this S bar is at 0 volts, let us say. So there is this is at a low voltage. So here you have a channel. And similarly, if this is so here you have a channel. Okay, this one is at 5 volts. This one is at 0 volts. Just 1 minute. Yeah, sorry. So,
Excuse me, sir.
yes.
So when S is 0, the terminal T2 should have a channel. Why
When
S is 0?
When S is 0, so when, let us see, A is at 5 volts, right?
Yes, sir.
So this is at 5 volts, S is 0. So this is at 0 volts.
Yes, sir.
So rather oh my God. What is the other? Yeah, sorry. This is at 5 volts. Actually, you have you have the wrong kind of potential difference. So there will be no channel. See, if you remember the operation of this NMOS, if the source is at a low voltage and if the gate is at a high voltage, then you have a channel. But this is the opposite situation. Here gate is at a low voltage, drain is at a high voltage. So you don't have a channel, right?
Yes, sir. Yes, sir. Got it.
So this is, you don't have a channel here. So this is an open circuit. All right. Now you just consider the other case. So now here S is high, so S bar is low. So now this is at a high voltage, this is at a low voltage for a PMOS. So here you have a channel. Okay. So this one is, T1 is on. All right. T1 is on. What about T2? This is at a high voltage, this is at a high voltage, no channel. But you do have a channel through this. All right. So as you can see, the PMOS is transmitting, the PMOS is good at transmitting a high value. Okay. See, when this is 0, it is an open circuit. But when this is high, when this is high means, of course, S bar is low. But this PMOS is good at transmitting a high logic value. So this is okay. It is transmitting this. T2 is off. All right. But because you have one of these paths, so you have a closed circuit between A and B, right? And you can now just do the same thing, same kind of analysis for so now let us say that you have A is at a low voltage. All right. Sorry. A is at a low voltage and S is 0. Okay, so S is 0. So S is 0 means this is at a low voltage, this is at a low voltage. All right. This is at a low voltage. So no channel here, and this is at a low voltage, this is at a high voltage. No channel here. So both are off. So you have open circuit between A and B, and you consider the other case. This is at a low voltage.
Sir, when A is 5 volt and S is 5 volt, why is T2 not conducting?
When
A and S both are 5 volt. Why is
when A is, so you're considering this one?
Yes, sir.
So yes. So what is the potential difference 5 volts and 5 volts, potential difference is 0. Right?
Okay, sir. Okay, sir. Yes, sir.
So no channel. All right. So now you have this one. So now this one is okay. So what you find is that basically when S is 0, this transmission gate does not transmit. Both cases it is open. All right. And when now let us consider the other case when this is at 5 volts. So we are considering the other case. So when this is at 5 volts, let us say. So when this is at 5 volts and A is at 0 volts. So A is low, this is high. So now you have a potential difference to form a channel. Okay. So and by the way, this is high. Now so now you have a potential difference to form a channel. So here you have a closed circuit. Okay. So now here T2 is yes. T2 is conducting. What about T1? This is so this is at 5 volts. So this is at 0 volts. So yeah. So this is 0. This is 0. No potential difference. So this is not conducting. And this is so because this is conducting, you have a closed circuit between A and B. All right. And this is low. So what you can see is that a PMOS is good at transmitting a logical 1. Okay. So PMOS good to transmit logical 1, and NMOS good to transmit logical 0. All right. So I think you understand the operation of the transmission gate. Is it okay? Hello? Is it okay?
Yes, sir.
Yeah.
All right. So yeah. So now let us just look at this. So this is the symbol for a transmission gate. Okay. This is the symbol for a transmission gate. Now this is a circuit which is built using a transmission gate. So can you understand the operation of this circuit? So what you can see is that this one, the upper one and the lower one, the upper one and the lower one. Okay. So these are these are controlled by complementary values of S. So when this is transmitting, this is off. When this is transmitting, this is off. All right. So as you have seen, so what is the value of X? Can you write down the value of X? So it transmits. When does it transmit? So when will it transmit A? When S is high or S is low? Yes?
When S is high.
So when S is high, yeah, so as you have seen in the previous slide, transmission happens when S is high. All right. For this circuit, so S is on the that NMOS. All right. So yeah. So this is S and this is S bar. right? This is S bar. So this is the working of. So what is this circuit called? This is called. So it is selecting either A or B depending on the value of S. So this is called a multiplexer. So this is a multiplexer built using transmission gates.
So CRM, I think we should stop today because
Yeah, we are done
that
for today. We are done for today anyway. So I think, yeah, so that is the end of it. Yeah, okay. We can stop here.